Okay, let's get started today. We'll start with some announcements and then logistics, then questions from last chapter, so chapter 3, and then we'll move on to the new material. So a few announcements. Let's see. I think a couple of you have taken advantage of this, but if you haven't yet, just once again, the Center for Student Learning just sent an email. They're happy to help folks. So a few of you have attended already, but they have hours pretty much all day, every day. You can set up an appointment virtually and stay as long as you like. I've mentioned a few tutors that I know are good: Chloe, Monique, maybe Lauren. So, and then Hope Florence, who runs the center. But you might find one that you like and just check out their hours. Okay, next thing, nice job on submitting your first challenge problem. Your second one is coming up already. So that'll be due on Wednesday. It's in your Oaks. Same information, same Google Doc. Access it the same way, but pick a different problem this time. And there's, I think it's challenge number 7 or 8, which are at the end of chapter 4. So we're going to start chapter 4, get through as much of that as we can, and get you well on your way to do that problem. Yeah, next comment I think is I've had a few questions about, a few email questions by email that made me think it is helpful if you guys read your journals like it is a book. I think that'll be really helpful. Instead of just like kind of flipping through, seeing what you need, start beginning page 1 of chapter 4, read it through the pages that were covered. There's, again, a few sections that we aren't going to cover in chapter 4, but we'll get to that later today. Okay, so maybe now it's time for questions from you guys. So let's first start off with any logistics questions, you know, when something's due. Oh, I should also say thanks to a few folks who noticed that one of the assignments, I think I had an 11:59 a.m. date. I forgot to change that. So please, when you see that, just shoot me an email and I can change it for the rest of the class. But remember, like the live, Amy, makes sense. Sometimes the electronic one doesn't. So if you feel like, hey, this doesn't make sense, every time in the live class she's saying they're due 11:59 at night, and here's this one due and it says I'm late even though I turned it in at 2 o'clock in the afternoon. Remember, electronic Amy makes a lot more mistakes. So just shoot me an email and I can correct that for folks. Okay, thanks, Elise. We will, yeah, if you guys want to put in the chat any content problems you want us to work on, just put them there and we'll work through them. And Brian, thank you for reminding us about the final exam. Yeah, so our final exam for 105 is during our allotted time. So, you know, every class when we would meet, which is ours is on Monday, Wednesday, 4 o'clock to 7 o'clock time slot. So that if you look down the final exam schedule, then ours turns out to be on Saturday, December 12th, 3:30 to 5:30. So it's just a 2-hour window. They've shortened that. And we have to do it live during that time. The departments in the college are still trying to figure out details about how we're supposed to administer these exams. So they keep changing things. It's kind of all over the place. But once they settle on that, then I will get that information to you. But what we do know is, as Brian said, it is live during that time. So you have to be available then and have good Wi-Fi, good internet. I'll give you more details about the specifics as we get closer and as the department decides. Okay, any other logistics questions or comments?
Exam that will be live on Zoom?
The final exam?
Yes.
So again, they haven't given me details. I'm sorry, who asked that question?
Macy, I'm sorry. I just missed the date you said.
Yes, so it's in the chat. So if you can go over and Zoom in the chat, you'll see the list of questions. So it's, Brian did a nice job reminding us. It's there for everybody. December 12th, which is a Saturday, 3:30 to 5:30. And it will probably be some combination of Oaks and possibly Zoom. We have to do some sort of browser lockdown thing. We'll practice as we get closer, but there will be details about that. So they're just very concerned about the integrity of exams. So they're making different regulations for us. So it will be through Oaks, but there may be some component where you also have to use Zoom, or maybe I'll live proctor it through Zoom and you all have to be there sitting at sitting in your room or at a desk or something, taking it live so I can see that, you know, it looks like there's software actually that monitors your eye gaze. And anyway,
Thank
won't
you.
get into all that.
I also have a question. So I know there's like reviews after each chapter, but do you know if we're gonna have like a final exam review?
Yeah, who's asking this?
Elise?
Elise, thank you, Elise. Great question. So I know we're just like racing through this class. I think we're already like halfway done, right? So that's a kind of incredible. And so as we get closer to the final, which is only like a week, next week or two, I will be having material towards what Elise is saying. There will be several practice quizzes that are optional that'll help you prepare for the final. There will be handouts PDF files that you can download and take a look at, things to help you prepare for the final exam.
Thank you.
Great question, thank you. All right, well, if you think of more logistics questions, put them over there in the chat. Just make sure it goes to everyone, that way we can all see, or unmute yourself when there's a pause in class. So we will start with these questions. So there's a couple that you guys would like to see on page 235. We'll go over those. If you don't have any more questions, then we'll jump into chapter 4 and get as far as we can and get you guys well on your way and partly done your homework. So if you think of more, put them in the chat. So we're going to go to Elise's question first. This is on page 235 in your journals. Elise wants us to look at number 2, and Will wants us to look at number 3. These are great questions to go over. Thank you guys for suggesting them. Okay. Does that work? Just make sure I don't write over about there. Okay, so we want to find number 2 and number 3 on page 235, the action points and the intervals of concavity. So we want to know where this thing is concave up and concave down. And all these problems, because we're visual learners, let's graph this function and get an idea for what it looks like. So I'm going to share the screen. Go to Desmos. Again, you could be pulling out a TI calculator. Y equals ln of 4 plus x squared. Okay, so there's our function. We have this little dip. We want to know where it's concave up and concave down. So concave down, oops, parts of a frown. So looks like we're frowning from, you know, minus infinity all the way to maybe somewhere around in here, -4, -5, -3, somewhere there. And then we switch to concave up, part of a smile, until, you know, it looks symmetric. So maybe again actually maybe here it looks like the 2, 3-ish in somewhere in there, and then it switches again to concave down because it's part of a frown. So we can see visually what we expect. Now let's go over the calculus to verify that. You didn't have to do any of that visualization to start this problem. You could just start it right off, head down, cranking away with your calculus. And so intervals of concavity have to do with the second derivative. So we have to get the second derivative, which means we have to go through the first derivative. The only way to do that, there's no way to just jump right down to the second derivative. So we have to get a first derivative. The derivative of ln is the derivative of the stuff over the stuff. So you rewrite what you're taking the ln of, 4 plus x squared, and then you put the derivative of that in the numerator. Okay, now probably Lisa's question was like, now we have to take the derivative of this function, and this function is a fraction, and we don't have in our list of differentiation toolbox that we've been putting over here, all those differentiation rules, we don't have one that involves a fraction, and yet this is a fraction. So there has to be some way that I can manipulate this and make it fit one of the rules we do have. And so if I write it like this, I took the 4 plus x squared, put it in the numerator, so it crossed the bar, so now it becomes with its exponent form to raise to the -1 power. Now we really have a first function times a second function. Now we can use the product rule. So the product rule is the first function times the derivative of the second function plus the second function times the derivative of the first function. Some of these boxes are easy because you're just filling in copying boxes. So the first function is 2x. The second function is 4 plus x squared to the -1 power. The derivative of 2x goes back here, that's 2. And then what goes in here, 2 prime, this is one that we did in the videos and once in a live class. So let's just put it over here though. In our differentiation rules, there's something called the general power rule. If your function, if y is a function of x raised to the n power. So in this case, the second one, so if we're just trying to take the derivative of 4 plus x squared all to the -1, that is something in parentheses raised to a power. So it fits this general power rule. It's like a power rule, but instead of just x in that parentheses, it's 4 plus x squared. And so I take it, then the derivative is, it starts just like the power rule, times the power down a power. So n f of x, take it down a power to the n minus 1, times the derivative of what's inside, times f prime of x. Again, this is called the general power rule because it's just a generalization of the very simple power rule, which is if y equals x to the n, then y prime is times the power down a power. So very similar. Again, you see the structure. The part that's kind of new is times the derivative of what's inside. And so we're going to use this general power rule, and that goes right here. So I'm going to take the function in parentheses down a power. So that's times -1. Take that thing in parentheses down a power, takes it to the -2, and then multiply it by the derivative of what's inside. Oops, x squared. The derivative of 4 plus x squared with respect to x is 2x. All right, so let's just summarize where we're at. This is a pretty long problem. Find the IPs and intervals of a concavity. The only way to do that, both of those questions, inflection points and concavity, have to do with the second derivative. To get the second derivative, you have to go through the first derivative. That wasn't too bad, but it's the next step, getting the second derivative that involved the product rule and this general power rule. And now we're supposed to do what with this second derivative? What's the point of getting the second derivative? Well, when the second derivative is equal to 0, we know the x's that make that a true statement. Are they possible inflection points or actual inflection points? When your second derivative is equal to 0, you're going to get possible inflection points. And then we'll determine if they are actual inflection points by doing the f double prime line. So we have to do a little work to get our PIPs. And then we're going to take our PIPs and we're going to put them on an f double prime line. However many PIPs we have. If we had 3, we put them all on this f double prime line. It divides the line into 4 segments. We'll pick a point from each segment, plug it into the second derivative, check whether that second derivative is positive or negative. If we had something like this, plus, minus, plus, plus, we would be able to interpret it as concave up because the second derivative is positive. from minus infinity up to this first PIP. It's also concave up from the second PIP all the way up to infinity. We'd also be able to come back and say, this possible inflection point is an actual inflection point because it changed concavity. And this other possible inflection point is an actual inflection point because it changed concavity. Okay, so that's the big picture, but we have to do a little bit more algebra to get there to fill out our PIPs. So questions so far? Okay. Okay, so let me do some arithmetic here, some algebra and simplifying. Let's see, I have a 2x times a 2x times a minus 1. So I'm going to have a minus 4x in the numerator. I'm going to bring this 4 plus x squared to the denominator. It becomes 4 plus x squared squared. Plus the next fraction is 2 divided by 4 plus x squared. I need to solve this equal to 0. Well, we're not good at solving two fractions added together equal to 0, but we are good at combining them into one fraction. And so we're going to get a common denominator. This is the same thing as minus 4x over 4 plus x squared squared. And then this is the same thing. I'm going to multiply it by another 4 plus x squared. All right, now that I have a common denominator, I can take those two fractions and turn them into one fraction. So in the numerator, I'll have a minus 4x, a plus 2x squared, plus 8, all over 4 plus x squared squared equals 0. Now, a lot of work, but we're all already to the place where we're almost there. We can almost do a PIP, figure out what the PIPs are. The only time a fraction equals 0 is when the numerator equals 0. So first week with the pretest, we learned this. Oh, I forgot a square there. 2x squared. Okay, so I need to solve that equation in red, but at least that's much better. It's not so intimidating to look at. It's just a quadratic equation. 2x squared minus 4x plus 8 equals 0. Well, I'm going to see if I can factor out this 2. And that might make the foiling easier. That's not going to factor though, right? 4 and 1, 2 and 2. Yeah, that doesn't factor. We need to use the quadratic formula. So let me solve this real quick. I feel like I've done something wrong with my arithmetic and I erased it everywhere. Let me do something else, just so we can finish this one. Okay, they should be at -2 and 2. So again, I've done something wrong with my arithmetic. And let's check on Desmos again. Sharing the screen, back to our graph. And so I was saying maybe somewhere around here, it looks like it's changed from concave down to concave up. And so here's -2. That's what it should be. So again, I made some arithmetic error in getting to this equation. There's something off about that. But let's continue the problem as if I hadn't made that error and we got to here. F double prime of -2 and 2. There's only 2 PIPs. We're wondering, are these 2 PIPs actual IPs? And this F double prime will also answer the question about concavity. So we pick something like -3 and plug it into the second derivative. Oh, I erased that too. It should be, it's going to be negative plus negative. So we pick something from each one, plug it in. When you have a sign change, this PIP and this PIP become actual IPs because you changed from concave down to concave up to concave down. And so our answer would be your concave down from -infinity to -2 and from 2 to infinity. Your concave up from -2 to 2. Okay, we got a couple more concavity questions. So I'm going to go to Bridget's next, and then we'll come back for Will's. Okay, Bridget's question is, for this function, she wants to know where it's concave up. First of all, this is a parabola opening up, but shifted up to 1. Can't visualize that. Use your tech tool. X squared plus 1. Oops, plus 1. All right, so that graph in red. Where is it concave up? Well, from the graph, it looks like it's concave up everywhere. It's always part of a smile. But let's see what the calculus says. So concavity, that's your keyword for second derivative. So you have to do that through the first derivative. F prime of x is 2x. F double prime of x is 2. And you're supposed to say, if you wanted to find possible inflection points, you'd set the second derivative equal to 0. Is there ever a value of x, and this is probably what Bridget's question is about, is there ever a value of x that makes 2 equal 0? No, so there are no PIPs for this problem, but that's okay, because the function doesn't change concavity. It is concave up from -infinity to infinity, or if you want to write it, it's concave up everywhere. And so there's no places where it changes, therefore, and we see that because there's no PIPs, which means there's no inflection points. Great question, Bridget. That's a good counterexample for us. Okay, the next question is, okay, Will wants us to go over number 3. This is a good one to practice. Will has us doing because we get to practice a couple differentiation rules. And it's probably something you're going to see again. Just a hint for something you might see on the final exam. Same question. Where's your concave up and concave down? But the function is different. The function is x e to the x. This is a good one because it gets us to practice a couple rules that we do need in our toolbox. Elisa's question number 2 from that page. That's a little long for a final exam. I might maybe start you in the middle of something like that, like I would do some of the work. give you the first derivative, maybe even give you the second derivative, maybe even give you the PIPs, and then you have to take it from there. But something like this is doable. This question isn't quite as long. It's doable on a timed final exam where we only have 2 hours. Okay, so same instructions. Where's it concave up and concave down, and IPs. So we need to get some derivatives. We have a first function and a second function. Therefore, we need a product rule. First times derivative of second plus the second times derivative of the first. Fill in some boxes. Take some derivatives. You can leave it like that and take the second derivative. So again, this is just x, e to the x plus e to the x. The second derivative is what we really need. Just to review, what does the first derivative help you get? First derivative helps you get where it's increasing or decreasing, critical points, tangent lines. That's it. We're going to add a couple more things to that today. Second derivative gives you where you're concave up, concave down, possible inflection points, actual inflection points. All right, so we need the second derivative. We have to take a derivative of this plus this. So we're going to have something plus something. Well, let's take the derivative of e to the x. That's just e to the x, e to the power rule. Rewrite it and then multiply by the derivative of the power, which is 1 in this case. And then we need right here in this long line, this is the derivative of x e to the x. Well, look, we already did that. The derivative of x e to the x was x e to the x plus e to the x. So you could do another, if you wanted, you could do another product rule, right? First, second, and that would all go right here. But you get the same place. Okay, so now we have x e to the x plus 1, 2 e to the x's. Okay, and our goal now is to set this thing to 0. Why do we want to set it to 0? Because any x that solves this equation, right, this equation in the red box, any x that solves this is a critical point? No, is a PIP. Any x that solves the second derivative equals 0 is a PIP. Thanks, Victoria. Welcome back. And you're welcome, Bridget. Okay, so solving this equation looks kind of difficult, but it actually has a nice, it factors, right? So we can take an e to the x out of this. So e to the x times x plus 2 equals 0. Well, there's really 2 factors. The only way 2 things can multiply and be 0 is if at least one of them is 0. So we'll set them each to 0. So we'll have e to the x equals 0 and x plus 2 equals 0. Well, the nice thing about e to the x or e to the anything equals 0 is that has no solution. No value of x is ever going to be exponentiated and make it 0. So then the next one, easy to solve, x equals minus 2. So x equals minus 2 is your PIP, right? Because that was the second derivative equal to 0. Now we're ready to do an f double prime line. Okay, we'll squeeze it in right here. F double prime. We only have to put one PIP. That's going to make this a little bit simpler problem for us. Pick something to the left, something to the right, plug it into the second derivative. Maybe I try -3, maybe I try 0. When I plug -3 into the second derivative, you can plug it in here, or here, or here. I think it's easiest to plug it into the part in the blue here. When I plug -3, I'll have e to the -3. Type that in on a calculator, but you'll see that's the same as 1 over e to the 3. So that's positive. That's definitely a positive number. And then -3 plus 2 is negative. So I have a positive times a negative results in a negative. The important thing is that means it's concave down on the interval from -infinity to -2. And then we're going to try something like 0, That's in the second interval from -2 to infinity. I pick any point. They're always evaluate to the same. I chose 0 because it makes it a little bit easier. E to the 0 is 1. 0 plus 2 is 2. So 1 times 2 is 2, which is positive. Again, I really just care about that sign. So it's concave up from -2 to infinity. And therefore, one last thing. So we answered the intervals of concavity. If we wanted to write that nicely, we'd say it's concave up when x goes, or x bigger than -2, so that would work. And then it's concave down when x is less than -2. And then we do change from concave down, part of a frown to concave up. So therefore, it must mean that -2 is an IP. We did all of that head down, pencil and paper, or pen on whiteboard, without thinking about the picture of it. So let's just check our work, because that was a lot of work. Let's enter our function, which is, whoops, x e raised to the x, whoops. Okay, and so we're saying that there is an inflection point at -2, so that'd be right here. So you're concave down from -infinity to -2, and then right here at this point, -2, you're going to flip and be part of a smile from -2 to infinity. So all that looks accurate. All right, great questions, Elise, Will, and Bridget. And those are good summaries because we got to practice differentiation rules, which are in chapter 2. Those are the main ones we need. Power rule, product rule, e to the x, ln x. We got to do all of those. Perfect examples. And then we got to practice first derivatives and second derivatives. So now we're ready to go on to chapter 4. Last chapter in this journal. And this is where all the main applications come. If you have more questions, please just keep putting them in the chat. But for now, we're going to move on to today's lecture and try to get through as much of chapter 4 together as we can, so that it makes less time for you on your own doing homework. So we got a good hour and a half. You guys give me undivided attention, focus, and I'll do the same. We'll give you everything we got so we can get as far as we can into chapter 4. Okay, chapter 4, just to point out a few things from page 285. All right, so in Journal 1, Chapter 4, the first page is page 285. We get some pictures of applications that we're going to tackle. And so the first ones on this side, we have a function, and we want to find what are called local extrema, local max and local min, and global max and global min. The other types of problems are something called constrained optimization, which you'll notice is a three-dimensional function. We're not going to actually cover those. And then the last one, maybe maximizing curvature. We didn't do curvature back in chapter 2, so we're not going to do that. So we're just going to focus on these two, what are called local extrema and global extrema. They're going to help us solve some challenge problems that we'll see at the end. That's your next challenge problem that's due this week. Okay, so flip the page, page 286. We're going to learn about extrema. So first thing on this page is it is vocabulary. We want to make sure we understand what these terms mean. All right, so here's a function I've drawn. First thing, we don't usually see these when they're given as explicit functional forms, because look at this weird little point here. Remember that thing was called a non-differentiable point. It was one of those cusp or corner points. Most of our functions are nice and smooth and continuous everywhere. This function's still continuous. I can trace it without picking my pencil up off the paper, so that's good, it's continuous, but it is non-smooth at this particular point, or non-differentiable. Because remember, if this is a roller coaster, I would sail off in this direction, riding in the forward direction. From riding the roller coaster in the backwards direction, I'd sail off in that direction. Those two directions don't match, therefore it's non-differentiable. Every other point on this graph, riding forward or backward, the tangent is the same, creates the same line. Okay, but it's okay, we can still ask questions about, even though we don't have explicit functional forms, y is a function of x, this is x cubed minus 4x, something like that. It would never look like this for polynomials, but we can still answer some questions. And so the first type of thing we want to do in chapter 4 is understand our vocabulary for a local extrema. Extrema just means extreme in either direction, so you can be an extreme min or an extreme max. And so extrema is one word that covers those two cases, max and min. We're going to have local max and min and global max and min. Local max would be something like this. This point right here is a local maximum. A local max, because at this point, if you were to stand and look all around, you'd say, yes, I'm bigger than my neighbors. If you're bigger than your neighbors, you're the biggest locally, that makes your local max. That's as opposed to biggest overall over the entire domain of this function. This guy right here is a global max because it's bigger than everybody on the whole domain. Local is also sometimes called a relative max, and global is sometimes called an absolute max. Just synonyms, common terms, similar terms for the same thing. Okay, so local just means nearby, near your neighbors, you're the biggest of your neighbors. And then global means you're the tallest overall over the whole domain. And then min, this would be a global min. It is the smallest value. And when we're talking about max and min, we're talking about y values, heights. So this was the smallest, there's nothing smaller than that. And then there's a couple local mins. This one's smaller than its neighbor, but it's not the smallest overall. This one's smaller than its neighbor, but it's not the smallest overall. Okay, so in this chapter, these are the two types of problems we want to solve. We want to be able to, given a function, not just pictorially, but given something like y equals 4x cubed minus 4x squared plus 4, we want to find the global max and global min of that function when it's given explicitly. And we want to find the local max and local min when it's given explicitly. So those are the main two types of problems that we have left to do this chapter. And there are two different techniques that we're going to use to do them. The neat thing is, though, you actually already have all the sort of computational machinery to do both types of problems. Okay, so questions for me about just definitions for local extrema and global extrema. Okay, we'll move on then. All right, so that's just vocabulary. You're going to practice. There's a couple more activities. And now we're going to go to page 289. There's a picture of Fermat, a mathematician, actually was a lawyer by training and then decided in his 30s he liked math, he was going to take it up. And he came up with a couple of neat ideas that we're going to use in this chapter. So this is page 289. Okay, this was Fermat's theorem. He said if some x value is a local extrema, which again just means it's a max or a min, it's the tallest or smallest of its neighbors, then it must mean that the derivative at that point is 0. Well, another way of saying that is then, like this is exactly the same thing as saying then x equals a is a critical point, right? If your derivative is 0 there, it means you're a horizontal tangent line, therefore you must be a critical point. So I don't have that, I erased the picture we just had up, so I'm just gonna make a new little one over here. Maybe it was something like that, I don't know. And it says, if your local extrema, so we had a local max here, a local min, and a local min. Those were our 3 locals. And Fermat's theorem holds. It does work for this example because here is a local min where it is a critical point. Here's a critical point. Here's a critical point. We have a horizontal tangent line at local extrema. You can draw as many different graphs as you want, and you're going to see that Fermat's theorem holds. It has to. It's a theorem. It has to hold for all functions. So long as x is a local extrema, it must be that there's a critical point there. And hopefully, again, that makes sense to you because local extrema are these like riding uphill, pause momentarily, you're temporarily horizontal, and then downhill again. And the same thing for local min. Going downhill, you pause for a moment, and then you're back uphill. In that pause, you have a horizontal tangent line. All right, so then what it turns out is that Fermat's theorem tells us that CPs are good places to look for extrema. So that's sort of the main conclusion that we get from this, is that CPs are good places to look for extrema. And we're going to just focus on local extrema now, but we'll also get to global extrema maybe half an hour later. In both cases, CPs are really good places to look for extrema, but they don't necessarily guarantee that you actually have an extrema there. And why would that be? Let's think about y equals x cubed. Well, let's do, actually Bridget had one that was kind of similar. Let's do y equals x cubed plus 1. Okay, here's a CP at 0. How do I know that's a CP? Well, I take the derivative of my function, x cubed plus 1, the derivative is 3x squared. Set that to 0, x equals 0 is a CP. And we can see that on the graph. Just right there, you would level off for just a moment, and if you zoomed in, zoomed in, zoomed in, zoomed in, you would be horizontal and flat right there. And this CP is not a max or a min. So just because your CP doesn't guarantee your max or min, but oftentimes CPs are good places to look for max or min. So many times it's the case that the CP actually is an extrema, but not always. So we have to check. We're going to get our CPs, and then we're going to check, is it actually a max or a min? Okay, so questions for me so far? Okay, we'll move on. We're going to go to page 291 now and do the first derivative test. So this example is actually, I should have wrote this is on page 294, number 1. So this is actually one of your homework problems. So we can work it together. You can write it down there in your journal and get part of your homework for this week done. Okay, so in this is a typical question. Again, this is sort of the culmination of book 1, which is these types of problems. Find the max or min or for a function. And this time we're going to find the local max or min for this function. They don't always have to have them though. So let's go back to Bridget's function from earlier. Y equals x squared plus 1. This one does have a local max that is also a global max, right? That's okay. That locals can be globals. It does satisfy Fermat's theorem because it is a critical point. There's a horizontal tangent line there. That local min is the global min, but there's no global max, right? It just keeps on rising and rising, and there's no global max. If they were over the entire domain, if they were to say, well, just focus on the part of the function that goes between -1 and 1, then we would erase any part of the function outside of that. So I go from here to here. This part of the function is the only part I care about. Get rid of this, get rid of this. And then I could say, actually, there are global max on this function. Mine's not very symmetric. This should be a symmetric parabola, right? So there's a tie. There are 2 global max when the function is restricted to live on that smaller domain from -1 to 1. Okay, so again, the moral of that story was for Bridget's function, if the domain is the entire function, you may not have global extrema, and that's okay. All right, but for this one, we want to find local extrema, and we're gonna, well, let's go and visualize that first. Let's take a look at what this thing looks like. Back to Desmos, change the function. It's a nice polynomial. These are, again, what you typically see in calculus are these polynomials, which fun to take derivatives of, right? Those are the easy ones. Bunch of power rules, sum and difference rules, constant rule, but you don't even think about them by the time you've done a few of these. Let me zoom out a little bit. Okay, so we have this, a couple terms in there, this cubic function, and we're looking for local extrema. Well, we can see from the graph, if we go from -infinity to here, there is no global min, but there's a local max right here at -116, a local min at 3 - 16, and then no global max. So we're going to try to get these 2 right here and right here. Hang on. Let's see. My dog's freaking out from the thunderstorm. Okay, let me just put her under cover here. Okay, so we know what this graph now looks like. We kind of have an idea for what we should expect, but we don't need to do that. We can just apply the calculus and get straight to the next step, which is finding these local extrema. Good places to look are critical points. So let's get the critical points. Again, nice derivatives to take. Looks like that might be a nice one to factor. We can take out the 3. Let's see. Hopefully this factors. 3 and 1. Let's see, minus plus, I think. Does that work? X squared minus 2x minus 3. Okay, so yes, so this factors. So we get 2 CPs, a CP at x equals -1 and a CP at x equals +3. Hang on one second. Come on, Chicha. Come on. Chicha. Go see John. Okay. So when we have these 2 CPs, they're good places to look for extrema, but how do we decide if -1 is a max or a min, if 3 is a max or a min? Well, the neat thing is there's nothing new here. Watch. we're going to be just doing an f prime line, something you already know how to do, single derivative, right? We're not asking about concavity. And we're going to put our CPs on there in order because they are a number line. This divides it into 3 sections. I'm going to pick a point from each section. That's going to tell me where it's increasing and decreasing. I know if it goes from increasing to decreasing, that CP must have been a max. I know if it goes from decreasing to increasing, that CP down here must have been a min. So we have all the information we need. It's just a matter of interpreting something we already know how to make, the f prime line. So I picked something like -2 over here. So I'll try f prime of -2, f prime of 0, f prime of 4. I plug into the first derivative because I want to know about increasing and decreasing. So let's see, f prime of -2, it might be easiest to plug in here. Let's see, that'll be a negative number times a negative number is a positive. That positive does not mean concave up. That positive means increasing because we are an f prime line. I'll label that over here in red. F prime. That means it is increasing. Then we'll try 0. So we'll have a positive number, a negative number. That means that negative sign means we are decreasing on the interval from -1 to 3. And then finally, when we plug in 4 to the second derivative, right here we'll have a positive number, positive number, positive. That means it's increasing. Therefore, our function goes increasing, decreasing, increasing. Because we changed from increasing to decreasing, this CP gets an upgrade. It is a local max. And then we go from decreasing to increasing. So the CP at 3 is a local min. So nothing to memorize, just think about the picture. Let's see if this checks on the graph. So back to our graph, we said that we had a local max at -1, which we do. And you can also report the y value. So like how tall is that local max? That local max, to get the y value, well, on the graph, you just hit the point, right? So I can just hit a point and it'll show me. Well, at that point, -116, how did you get that? That's f of -1. So you're plugging in -1 here. You'd have -1 cubed is -1. -1 squared is 1 times 3 is -3. -1 times -9 is +9 plus 11. So that's 20 minus 4 is 16. So we have that there's a local max at the point -116, right? If you want to write it in XY point notation. Oh, sorry. So you can see a little better. I had plugged in -1 into the function because I wanted to get the y value, the height at -1. And I got this point -116. You can do the same thing for the local min if you want to give it in a point notation. Not only is it at x equals 3, it is at x equals 3 and y equals -16. And again, this f prime line, we see everything that's happening right there. It's increasing from -infinity all the way up to this point here at -1. Then from -1 to 3, we are riding our bike downhill. Now we're pedaling uphill. So we see all the information is given visually in the f prime line. So we're just adding one more piece of information today, is that the f prime line can tell you where your local min and your local max are. Okay, so let's make sure we have that down. Suppose your f prime line looks like this. Suppose for a particular function, I get 3 CPs, CP1, CP2, CP3. That divides the region into 4 intervals. I pick a point from each interval, I plug it into the first derivative. Suppose I have plus, plus, minus, plus. What is your interpretation then? Okay, well, we already knew we were increasing from -infinity up to CP2. We're also increasing from CP3 to infinity. We are decreasing from this little range here, CP2 to CP3. But we can say CP1, is that a max or a min? No, because we don't have a sign change. We're increasing and then increasing some more. That's like that cubic function, right? And then we do go from increasing to decreasing at CP2. So we can actually say this is a local max. And then we switch the other way, decreasing to increasing. So CP3 is a local min. Okay, so summary, local extreme are actually pretty easy. You just have to interpret something you already know how to do, the F prime line. Okay, let's take a little break. Questions for me. We'll take a few minutes just if you've got any questions on anything we've covered so far. We're halfway through this class, so let's pause for you guys. Okay, great question, Max. So Max wants to know for this function, what about the global extrema? Basically, he's wondering what happens there. And so, again, we're going to have two classes of problems, find local extrema, find global extrema, and we're going to have two different ways of doing those. So the instructions have to be very clear. In this case, they only wanted us to find local extrema. If they wanted to make it a global extrema, they would be very specific, and we're about to get to those. They'd say, find the global extrema for this function, for this interval. But you could answer this, Max. So at this point, we could say from the image, the graph, again, we precisely found these local extrema, but this graph actually has no global min, right? Because it just keeps on shooting down to infinity down here, and no global max. So you're getting that visually. The types of global extrema problems that we can handle and that we are going to do in maybe 10 or 15 minutes is we'll be able to do a function like this, but we have to restrict it to some interval of interest. We can't go like minus infinity to infinity. We have to say, okay, here's the interval we're interested in. Great question.
Can I ask a quick question?
Yes.
This is Lauren, by the way.
Thank you, Lauren.
But for the last problem, for the local max and local min, when you got, like when you saw that it was a local max at -1 and a local min at +3, was that just like, did you plug those numbers back into the original function in order to figure out if it was the min or the max?
Great question, Lauren. Okay, so there's two pieces to this. So Lauren's question is a good place for us to pause and make sure we can summarize. To determine, so like, first of all, these -1 and 3, those were CPs. Those were just good places to look for extrema. And then how we determine if they actually are extrema, and then which way, is if there's a sign change. So if there's a sign change, here we had plus minus and then minus plus. So both those CPs have a sign change. So they are going to be extrema. It's just to figure out which way they go. Is that extrema a tall one, a min, or is it, a max, or is it a min? So to be a tall one and a local max, it has to be that you were increasing and then you're decreasing. And so when you have a sign change from plus to minus, you're a local max. So you can either memorize that rule. So Lauren's got a good rule for folks that if you're having trouble like visualizing this just in your rule-based person, this is a great rule. Write down Lauren's rule for local max. If your F prime line stops at a CP and it changes from positive to negative, then it must be a local max. That is always, always true. That's a rule. Or you can think about it as, well, what does that plus sign mean? That means I'm increasing, I'm pedaling uphill. What does the minus sign mean? It means I'm decreasing, I'm pedaling downhill. So therefore, when I stop right at the top, at that CP, I have a horizontal tangent line, but furthermore, not as just a horizontal tangent line, it has to be a local max. Now, if you go the other direction, at the CP at 3, there is a sign change, and the sign changes from minus to plus. When that happens, you're decreasing to increasing, therefore you're a min. So second part of Lorentz rule, if your sign change around the CP goes from a minus sign to a plus sign, like it does in this case, then you must be a local min.
Thank you.
Thank you. That was a great question. Great way to summarize. Great. Okay, so we got plenty of time. So we have to cover a couple more things. We have to do the second derivative test, global extrema. So then we'll get to Max's question there to do more general problems. And then the last thing, like maximize profit, minimize cost. So we have a couple problems. So I want to get through all of those today, and then that'll be pretty much we got to do all of chapter 4 together live. So first derivative test helps you find local extrema. So that's another key thing. Like put that in your category or your study guide. If you need to find local extrema, you can do the first derivative test, or you can just make a little picture, right? This little picture should help you. This picture does a lot, right? This picture tells you where you're increasing and decreasing, and it tells you where your local extrema are. Now we're going to change this to the second derivative test. So this is on page 297. Okay, we want to find, let's actually do the same problem. The second derivative test is it's just an alternative to the first derivative test. So the first derivative test, you can use it to find local extrema. The second derivative test, you can also use to find local extrema. It's just another way. Rather than doing an F prime line, we're going to do things with the second derivative. And hopefully, again, this will make sense. It should be very straightforward. But if you're an algorithms person, there's these sort of algorithm pages. If you like to have the rules, on page 298, there's one of these gray boxes that's like step by step. You can do the second derivative test. And there's one of those for the first derivative test as well. I think that's a little earlier in the chapter. But yeah, a few pages back on page 292, these are the step by step things for the first derivative test. Or again, you can just summarize down with this picture. So for visual learners, maybe this helps. For folks that like to have step by step. All right, so first derivative test and second derivative test, you can think of those both as algorithms. So we're going to do the second derivative test now. But they're both ways to get local extrema, and you have your choice. So every semester, some students like one over the other. It's your choice. On the final exam, unless I specifically say use this particular test to find the local extrema, you're welcome to do it either way and to check your work. Okay, so let's just work through this problem. The second derivative test to find local extrema, well, probably because it got the name second derivative test, we're going to need the second derivative. So let's go ahead and do that. And let's keep some of the information that we did from before, which was that we found the first derivative gave us two CPs, CPs at x equals -1 and x equals +3. Let's get a second derivative. No problem. If I set this to 0, I'd be getting PIPs. I could use that to do an F double prime. I could use that to find intervals of concave up and concave down. I could use that to see if any possible inflection points are actual inflection points. So just a quick review, but we're not trying to do that in this problem. We're trying to find local extrema. And so why am I telling you to compute the second derivative then? Well, here's a neat property about a second derivative. So let's think back to that function we had, 20 minutes ago, something like this. We said this was a CP that turned out to be a, what does it look like in this picture? A local min. This was a CP that turned out to be a local min. This is a CP that turned out to be a local max. So to find these local extrema, CPs are good places to look. And we could use the first derivative test, but now we're going to add another way to do it with the second derivative. So what is in common with these local mins? There's two local mins in my picture. What can you say about the concavity at those 2 points? Is the function concave up or concave down at local mins? So just take a moment, think about that on your own. Type your answer in the chat if you like. At local mins, can you make a statement like every local min is always concave something? And then vice versa, for every local max, can you say every local max is always concave something? Right, so every time you could draw as many pictures as you wanted, as many local mins, and you'll see that this pattern holds. Every local min, right, you're like this. You are at this point down here on this knuckle is the local min, and you are concave up, a cup, hold water. Has to be the case. Anytime there's a local min, you have to be concave up. A good place to look for local min is CPs. So I could take every CP and decide, is it concave up or is it concave down? So that is the whole second derivative test. Again, you can go through on page 298 and go through those steps. Again, if you like to write steps and memorize those, or you can just think about this, that this picture here, every local min, just think what a local min is, has to be concave up at this point right here at this knuckle. It is a horizontal tangent line, and it's also concave up. So I'm going to take my CPs, because those are good places to look for local extrema, and then I'm going to check. At -1, is the function concave up or concave down? How do you do that? You take -1 and you plug it into the second derivative. Remember, that's a CP. So I take the CP and I plug it into the second derivative. If that turns out to be a positive number, I know it must be concave up, therefore it must be a local min. Let's see what happens. When I plug -1 in, I get -1 times 6 is -6, minus 6 is -12. I don't really care that it's a -12, I just care that it's negative. So therefore it is concave down at x equals -1. Therefore that concave down looks like this. That CP is a local max. You have a local max at x equals -1, which implies local max. And then Lauren's question, if you want to get the actual height on the graph, at x equals -1, you are local max, but how tall are you? You're taller than your neighbors, but like just how tall? You get that by plugging -1 into the original function, f equals -1, because you want heights on a graph, you do things with function. When you want steepnesses on a graph, you do things with the derivative. When you want curviness, like how bendy it is, you do things with the second derivative. Okay, so we wanted to know how tall it is. So that's a question about height. So we plug in -1 into the function. I get -1 cubed is -1. -1 squared is 1 times -3 is -3. -1 times -9 is +9 plus 11, +16. So we have a local min at -1, I'm sorry, a local max at x equals -1, y equals +16. Or if you like to write it as a point, -1, 16. And that's going to give you the exact same thing that we just did with the f prime line with the first derivative test. So this is just yet another way to do it using the second derivative test. Okay, so let's finish the problem. We had two CPs. We checked one of them. Let's check the second one. The second CP was at +3. So I'm going to plug that in. A CP is a point where you have a horizontal tangent line. So I've got some point in the air, horizontal tangent line there. I'm wondering, am I concave up or am I concave down? I answer questions about concavity with the second derivative. I plug in the point of interest, 3. So I'll have 6 times 3 minus 6 is 18, minus 6 is +12, which means because it's positive, it is concave up at x equals +3, which implies you are a local, you're concave up, so you're a local min. When x equals 3, you could get the corresponding y value by going back up here, and instead of plugging in -1, plug in +3. 3. 3 cubed is 27, minus 9 times 3 is 27, minus 27 plus 11, minus 16. So if you wrote it as a point, it'd be 3 minus 16. Again, all the same stuff we got by visually looking at it with Desmos. So just go back there one more time. Here's our function. Now we did a second derivative test. We stopped at this CP at x equals -1. It is a horizontal tangent line. If you zoom in more, it might look more horizontal. Yeah, little peak right there. And that peak is a max because we are concave down there, right? So it has to be max. On the other hand, over at x equals +3, we zoomed in and we are horizontal tangent line right there at that point. Yeah, there's 3 minus 16, and we are concave up there. Because we're concave up at a critical point, it must be a min, a local min. Okay, so pausing again. You can unmute yourself, ask any questions, type them in the chat. Any questions about anything we've done so far today? So we reviewed some stuff from chapter 3. We did first derivative test to find local extrema. We did the second derivative test to find local extrema, and we used vocabulary to know local extrema versus global. Okay. So it looks like there aren't any more questions. Again, if something comes to mind, put it in the chat and we'll pause and come back to it. But in the meantime, then we're going to move on. 2 more things we need to cover: maximum profit and then global extrema. So maximum profit, this is page 307, 308. There's a couple examples. I can also promise you this will be on your final exam. There will be a question very similar to this because this is sort of prototypical business calculus problem. Maximizing profit or minimizing cost is sort of the pinnacle of what we're trying to do in business calculus. Okay, so these are usually word problems. In this case, there's a bike shop and managers have decided they have a couple functions that help them describe how they should price bikes and then how much it costs to produce these bikes. So they have determined that to sell X bikes each month. Oh, I should also say, this just reminded me, whenever you need more examples, shoot me an email, we can do an office hour. We've done a couple, not too many folks have shown up, but you can also go back to the videos for not just this class and slow it down, but all the videos for this week. Like there's several more examples of these maximum profits. So again, if the one we do today, you're still kind of confused on, go back to those videos, watch them a couple times, pause them, try to work it out yourself. Many, many more examples of local extreme and global extreme will be in each week's videos. Okay, so the price of the bikes, if you want to sell X bikes that particular month, you should price them according to this function D. Now, this is a linear function, and so let's just throw in some numbers. Like if you wanted to sell 10 bikes, and you put in 10 here, it's saying you should price them at $960. But if you wanted to sell 100 bikes, you want to sell more of them, put in 100 for X. So we have 400, 1,000 minus 400, 600. So it's saying you can actually price them a little cheaper if you're wanting to sell more, right? That's kind of supply and demand. It makes sense. And we have this linear function. And there's only certain values of X that are going to make sense, right? It doesn't make sense to talk about selling negative 10 bikes. So the domain here is X equals 0 up to some other value that will make sense. Like what if you tried 300 bikes? If you wanted to try to sell 300 bikes, it's saying you almost have to give people money, right? Because you'd be going negative, like negative $200 per bike. So there's a range. X is 0 to 250 is what makes sense in the context of this problem. And so we're wondering, ultimately, they want to know how many bikes should you sell? I mean, this is really what they're saying. How many bikes should the shop sell to maximize profit, right? That's really what it's saying. Find the maximum profit. We'll get there. We'll do that too. But really the question is, how many bikes should this bike shop sell? So they really want to know what's X. X can go from 0 to 250. 0 doesn't make a lot of sense. 250 doesn't make a lot of sense. But somewhere in between there's this sort of sweet spot that maximizes the profit. Now, there's more than just the price of the bikes, right? I'm not just collecting money for bikes. I actually have to put out money because they have to be produced, and maybe have folks in the back that are doing this, and they need certain supplies. Maybe sometimes they can get those supplies in bulk, but maybe there's also some fixed costs associated with this because you have to pay those employees. So you can think about this 800 as like a fixed cost, and then this is per bike, $280. And the cost, again, they have two functions. So here was our price function and then our cost function. So to get a handle and get a sense of what this means, maybe you try throwing in some numbers, like if you produce 10 bikes, it costs you $2,800 plus $800, $3,600 to make 10 bikes. But if you're making 100 bikes, it doesn't scale up. It is linear, but then there's this fixed cost, right? So you can see that this cost, this linear cost function is somehow going to interact with your price function. And so the main thing to think about maximizing profit is so that was the first question. Find a maximum profit. Find a function that represents the profit. That's really what we need to do. So we need to create a function P. That is a function of X. So it'll be like, if you sell X bikes, how much money are you bringing in? You're bringing in some money when you sell one, but you're putting out some money every time you produce one. So we need to somehow figure out how we combine the D and C to make sense for a profit function. So this is the price per bike. So what happens if let's go back to that, if I wanted to sell, let's say 100 bikes, X was 100. The price should be 1,000 minus 400 is 600. So if I'm aiming to sell 100 bikes, I should put the price tag on them for $600. but that's just per bike. But if I had actually sold X bikes, 100 bikes, I'd make 100 times $600. So this, I'm gonna put this function up and then I want you to take a look at it and see if it makes sense to you. So our profit in this scenario, when we're selling bikes, it will be how many bikes you actually sell times the price per bike. So again, the price per bike depends on how many you're selling, but that example when X was 100, it would be $600 times 100 bikes. And then for making those X bikes, it costs you C of X. So it'd be C of 100. So you can just throw in some numbers till this kind of makes sense to you. Like some people try to just do D minus C, but that doesn't make sense. That's just the cost of, or sorry, the price for one bike, but you're actually selling X times that. So that's where we get the XD minus the CX. Okay, this is a function that represents profit. So let's plug in the numbers that we have for this bike shop. So we plug in our D function, we plug in our C function, we multiply the D function times X, do a little more arithmetic and simplifying. And let's see, then we'll have a minus 4x squared. What is that? Plus a 720 x's minus 800. This is our profit function. So down at the bottom, we have a function P that if you give it a number X for the number of bikes that you're selling, this will be how much you're actually making. Again, some money comes into you when someone buys a bike, but some money goes out because you had to pay employees and get the parts. This represents, you input an X. If there was 80 bikes sold, how much is the shop actually making? We can plug it into this function exactly and tell you in dollars how much you've made. Okay, so these first couple steps are what we usually call mathematical modeling. And for a word problem, that's an important step, is to model this English into mathematics. The mathematical modeling creates a function that is a profit function appropriate for business calculus, but it's actually a nice, this is why I keep saying we deal a lot with polynomial functions. This happens often in business calculus. You're combining linear or quadratic functions and you're going to get more polynomial functions. So we've done the first part where we found a function that represented the profit for the bike shop, but the next part is we want to maximize that profit. Well, now this is just like starting with, this is just an f of x, like just what we had been doing. Find the maximum of this function. All right, let's go ahead and do that. Maybe I'll erase the word part of the problem, so maybe like right here. Okay, we want to find the maximum of this function. Well, let's think visually about this. So let's go. Back to Desmos, put in our function that represents the profit for the bike shop. And it is a nice quadratic function. We probably got to zoom way out, right? Or give it to do a better scale. Let me try this also. I think this might have a smarter scaling, or your TI calculator probably does a better scaling too. Okay, so it is a parabola. We see that from the x squared part, and it's got the negative in front of the x squared, so it's a parabola opening down, and it looks like there is a peak. If we're just eyeballing it, you know, maybe like somewhere around 89, 90, right? That seems to be the tallest value on the graph. And then remember, we kind of discussed, like, it doesn't make sense to talk about making negative bicycles. So we start at 0, that's sort of our domain. Ignore this part here and ignore the part of the graph that goes over there. We're only interested when the function is positive. We want to make money, right? We don't want to lose money. So when you're below the x-axis, you'd be losing money. So we have positive profits, but we want to know what's the best, because you don't want to make too many bikes, because then the cost takes over, right? Then it starts swamping out how much you're bringing in. You're giving out too much for supplies or paying employees to keep building these things that you aren't selling. Okay, so we're guessing from the graph 89, 90, 91. So let's see if that actually happens with the calculus. So maximizing a function, this is, you know, it's a p, but it's just like an f of x. I'm sorry, was there a question? Okay. All right, so this is just like what we were doing before. We're finding the extrema of this function. We really want the max, though. We're not so interested in that min. We don't want to minimize profit. We want to maximize it. So we will take the derivative, because good places to look for extrema are at critical points. Critical points happen when your first derivative is equal to 0. So we'll take a first derivative, minus 8x plus 720, set it to 0. These are places where you have a horizontal tangent plane. So 8x equals 720, divide both sides by 8. X is, oh yeah, there it is, nice and easy, 90. Even number. Is that the max? No, that's just a CP right now. The calculus doesn't tell us it's a max. We have to do just one more step to determine if that actually is a max. You got two choices. You could check whether this CP is a max or a min with the first derivative test. That's your F prime line. Put your CP on there. Pick something to the left, like 80, something to the right, like 100. Plug them into the derivative, which is right here. Negative 8 times 80, what is that? Negative 640 plus 720, so that is positive. 100, so that'd be negative 800 plus 720, this is minus. We are increasing to decreasing, therefore this CP is a local max. Well, it turns out, though, on this graph that local is the global, because remember the graph. Again, we'll get to globals in a minute. Maybe 5 minutes. Okay, that's checking it with the first derivative test, but you also have learned now another way to find extrema is with the second derivative test. Maybe that's even easier in this case. So we have a CP at 90. The second derivative of P is minus 8. That's less than 0. We know it's concave down, part of a frown. Therefore, that CP is a local max. So we've checked it two ways. First derivative test, second derivative test. Both cases, we know we are max. That's what we were trying to do, maximize profit. So we know that if you sell 90 bikes, that's the optimal value. If you sell a little more than that, you won't make quite as much profit. You're still making profit, but not quite as much, because again, then the cost of supplies, labor, employees swamps out the price that you're making. Okay, so we'll pause here on this maximum profit problem. Again, that you will see this on your final exam. This is a central question for calculus.
Wait, so is the local max 90, or is that just the CP?
It is the local max. So 90 was the CP, and then we checked if the CP was a local max or a local min. CPs are good places to look for local max and local min. We checked it two ways. First derivative test, we put an F prime line. We saw that we were increasing and then decreasing, so therefore we could give the CP an upgrade and say it's actually a local max. Then we checked it with the second derivative test, which says take the second derivative, plug in, actually we should have done this. Take the second derivative and plug in your CP at 90, you still get minus 8, which is less than 0, which means you're concave down. part of a frown, you're that point on the knuckle, you're horizontal tangent line, but you're even further than that because you know about concavity, you must be a local max.
Okay, thank you.
Mhm. Okay, today's last topic, global extrema. I'm going to start, I think we'll start with page 313. All right, so we know what global extrema are by definition. We know what it means to find them visually. We're looking for the tallest and smallest on a graph. But something Max's comment reminded us earlier is global extrema. These problems are going to always be like this form. Okay, this example that I want to work is actually one of your homework problems on page 315. So something that's due in the drop box for the calculation problems. So we'll do one together. Maybe we'll have time to do another one. And then on page 313 is one of those gray box pages with the algorithms. So again, if you're an algorithms person, I want the step-by-step thing. And then if you're a visual person, we're just going to narrow it down to this table here. That's going to tell us everything we need to do these kind of problems. But back to, again, something Max reminded us of. His question or comment reminded me that global extrema, the problems are always going to be written in this way. They're going to be very specific. Find the global extrema of this particular function. But here's the part that they have to add on this interval. And they have to give you an interval, and the interval has to be closed. So you're going to read on page 309, 310, 311. You're going to read about a theorem called the EVT, the extreme value theorem. All right, so the EVT, pages 309, 310, 311, when you read this, the extreme value theorem says if your function is continuous on a closed interval. Well, again, in business calculus, almost every function we're going to have in this book, in any calculus book for business calculus will be continuous. That just means you can trace it. There are no asymptotes, there are no jumps, there are no breaks. Polynomial functions are continuous everywhere. So it's easy to recognize these nice polynomials. Those are the ones you like to take derivatives with power rule. And you could graph the function and see that it is continuous. If it's continuous on a closed interval, so we don't care what happens. There could be asymptotes, outside of this interval, but they have to give you a closed interval. So that's why these problems always have a continuous function on a closed interval because they're satisfying the two conditions of the EBT. If your function is continuous on a closed interval, then you have to have at least one global max and at least one global min. So this is what's called an existence theorem. It tells you whether or not it makes sense to go hunt for these extrema. Just to give you an example, so I'm an applied mathematician. I've worked as a consultant for different companies. It's probably been 10 years ago now, but I work for a company called SAS, a statistical software company. And they pay me a lot of money per hour to find extrema for them. But their functions were not just y as a function of x. It wasn't even just z as a function of x and y. It was like w is a function of a million variables, literally. And they wanted to find the local max and local min, and in some cases, global max and global min of this multi-dimensional function. And so it made sense for me before I was charging them hourly and taking money to say, does it even exist? Like, does a global max even exist for this function? And so I actually used a higher dimensional version of the extreme value theorem. I checked things, properties of the function. Was that function continuous? Was the region closed and bounded and finite? All these other conditions I needed to check. And then if they did hold, it made sense. I knew then that a global max existed and it was worth my time and their money to try to find it, right? Because it may not exist. Max showed us an example earlier of a function where it didn't have a global extreme. It just kept on going up. The max kept going, the min kept going down. So we want to know if it makes sense to hunt for them. That's what the EBT, the existence theorem, tells you. All right, well, does the EBT apply to this problem? Again, almost always textbook problems they will, but my concept questions on the test, this is something I want you to make sure you know how to check. So does it apply for this calculation problem? Does it make sense to find global extrema? Is your function continuous on a closed interval? So let's graph this function and see what it means. Is the interval closed? That just means it includes its endpoints. If it was written like this, say -2, this means don't include 2, get really close to -2, but don't include -2, do include +2. This one is not closed, right? Has to include both endpoints. So let me graph this and show you what we mean. Now we'll go back to Desmos. In this function, 1/3 x cubed minus x, and okay, so there's our cubic function, a couple turns there, and this function extends. There's no global min and no global max, so very similar to the question Max asked about earlier. Which reminds me, when I was in graduate school, we had a lot of international students, and so they're learning English, but they're learning that for the type of math I did something called optimization. So I was maximizing and minimizing functions a lot. And one of the international students, in fact, two of them, they named their babies Max. So that just reminded me Max, because they like to maximize functions. Okay. 1/3 x cubed minus x, but we want to only focus for this part of the graph from -2 to +2. So let me see if I can remember how to do this in nope, that's not it. There's like a parentheses, was it? Oh, yeah, here we go. Oops. Okay, so therefore what I did was I put a condition on this function. So I graphed x cubed minus x cubed, 1/3 x cubed minus x. I graphed that. That was the red function. And then I added this condition. So that's the full function in black. And then we'll turn that one off. There's the sort of truncated part where you're only focusing on one section of the graph. Notice that as that changes, like if I say from -2 to 3, we get more or less of the function, right? So they have to give you an interval and they have to include the endpoints. And what that means, including the endpoints, in fact, let's go ahead and leave it at 3. Maybe that's more interesting. When it says include the endpoints, what we're doing is we want to make sure that this dot right here, there really is a point And that's called an endpoint. It's your left endpoint, and then over here is your right endpoint. So like x equals -2 is your left endpoint, x equals +3 is your right endpoint. All right, so we have this section of the graph that we're focused on. I'm going to copy it here because we'll refer to it a couple times. Okay. Global extrema, again, it satisfies the EVT. We know we have to have at least one global max, at least one global min. Well, let's visually identify them. What is the global min? I'm not sure how accurate my graph is. Let me check one more time. Maybe they are tied. Okay, maybe my graph is decently accurate. Okay, it looks like there could potentially be a tie for a global min here and here. We're not sure, we're guessing. But it's pretty clear that this point over here is the global max. And that was when x was 3. At the point 3, something will fill that out. Over here, it looks like it might be a global min at -2, right? That was -2. And this one, maybe that was like 1. I'm guessing that was about 1 something. Okay, so just visualizing it, and then we'll talk about the steps in the calculus. If you don't have a graph or you can't graph it, or you're in high dimensional space like I was, like a million dimensional space, I can't graph anything there. Okay, so let's first get these y values, right? When x is 3, what is y? That's a height on the graph. So I go back to the original function, I plug in 3. So f of 3 is 1/3 times 3 cubed minus 3. So that's 27 divided by 3 is 9, minus 3 is 6. So this is the 0.36. And we can do that for -2 and 1. Let's see, -2 will have 1/3 times -8 minus a -2. So -8/3 plus 2, which is 6/3. So -2/3. So this, what we're thinking might be a global min is at the point -2 -2/3. One more point we wanted to check to see what it was. F of 1 is 1/3 times 1 is 1/3. -1 is -2/3. Oh yeah, so we do see that they do tie. So it looks like visually these are our global mins, that there is a tie, and that's possible. You can have ties because the EBT says at least one, right? So you can have more than one. So visually we're ready to answer the question, but now we need to do this with calculus. But I'm gonna pause before I get to the calculus and see if you guys have some good questions for me.
Yeah, I have a quick question.
Okay.
Did you just randomly choose 3 to plug that in to find the global min, or is that the global max?
Yeah, so
I meant global min and global min, like all of them. Like, did you just use 3 as a random point?
oh, good question.
-8.
So Lauren, what I was doing was I was going back to Desmos, so I was just trying to get a hint from Desmos as to where I thought these might be. And so back here on Desmos, I was like, I'm pretty sure these look like the lowest. So remember, global min is your lowest on this section of the graph. So we only went from -2 to +3. We're in this red part of the graph, and we're saying like, who's the lowest? It looks like this point here, which was when x was -2. And then this other point over here looked like when x was 1. So I was just kind of eyeballing it. And what I was doing when I plugged in, I was like, what is the y value there? So when x is 1, I plugged 1 into the original function and got -2/3, or -0.667. Over here at -2, where they're pretty close to -2, that point, yeah, there you go, -2, -2/3. And then the other one we were checking was here at 3, 6. And so we were visually saying, clearly that's the global max when x is 3, right, on the graph. And then I was plugging them in to get their heights.
Okay, thank you.
Okay, so visually we have a sense of there's a bigger graph, and then we zoomed in, and it's like we have blinders and we only care about this section of the graph. Stuff happens over here, but we only care about the given closed interval that they've given us. We just erase everything outside of the graph. And again, I gave you a way to do that in Desmos. That sort of zeroes in on just the part of interest. And then once you do that, you can visually check global max and global min. You're just looking for tallest and smallest. But again, we have to do more than visual. Visual is a great way to check your work. I encourage you to do it on your final exam. I encourage you to do it on your quizzes, but you have to show us the steps that show us the calculus. And the reason being because, well, some of you might go on and take econ, you might have three-dimensional functions there, and you can't visualize sometimes three-dimensional. You certainly can't visualize four-dimensional, five-dimensional, million-dimensional functions. So you have to understand the calculus that extends. Okay, so last piece of today, 10 more minutes, we're gonna figure out how to find global extrema with calculus. It's really gonna be pretty simple. Global extrema happen only at two places. So this is a key piece of the puzzle here. And you're gonna read this, when you read those 309, 310, 311, these pages are gonna help you come to this conclusion, that global extrema occur at only two places, CPs and EPs. All right, CP stands for critical point, EP stands for endpoint. Those are the only places global extrema can happen. Why is that? Well, CPs are places where they're good places to look for extrema, right? We already talked about that. They're horizontal tangent lines. You might be a max, you might be a min. Those maxes might be local, or they could sometimes be global. Like, look, this was one where you had a CP, and it's a global min. But these other 2 points are endpoints, and they turned out to be global extrema as well. Now, they won't always. Suppose I decided to stop the function right here and only use this part of the graph. Well, there is a global extrema at an endpoint, but not at this endpoint. This isn't a global max or global min. Right, so it depends on the interval that you're given. But this phrase right here is everything. We can actually create a picture or an algorithm based off that one sentence. So global extrema happen at CPs and EPs. Well, let's get to CPs for this function. Take a derivative, set it to 0. Derivative is x squared minus 1. So the CPs are x equals positive 1, x equals minus 1. You can factor this. So you have a CP at x equals minus 1 and a CP at x equals positive 1. Those CPs are good places to look for max or min. I could do a first derivative test, I could do a second derivative test, but that only tells me about local extrema. I want to know about global extrema. And then we also had some EPs. We had EP at the left endpoint is -2, and the right endpoint is at +3. It's important when you get your CPs to make sure they lie within your interval. Is -1, the CP of -1 between -2 and 3? Yes. Right, here's -1, that is between my interval. It's possible you could have got a CP that was like -10, that's all the way over here. That doesn't lie in your interval of interest, so you wouldn't include it. So again, that's a key summary. You'll see that in the videos for global extrema as well, but make sure you get that point, that the CPs only make it in a list if they lie between your endpoints. Now, you make a list of all the CPs and the EPs. There's always 2 EPs and they're always given. CPs, you could have 1, you could have none, you could have 7, right? So this problem only has 2 CPs. What we're gonna do is make a list now. Okay, first you're gonna start by putting your EPs in the list. The first EP was at -2. The second EP was at +3. Then you put all the CPs that you got, so long as they lie between those points, -2 and 3. So I got a CP of -1. Again, -1 does get to go in there. because it is between -2 and 3. Had we gotten a CP of +7, +7 is not between -2 and 3, discard it. That'd be all the way over here. That's not fair because you're only looking at this section of the graph. Okay, other CP is 1. Those are all X values, right? So I'm just making a table with 2 columns. I'm putting my EPs and my CPs. I'm only putting EPs and CPs because those are the only places that global extrema can happen. Now, what should my second column be? What should this column right here be labeled? What am I going to plug these points into to figure out who is the tallest and who is the smallest? Okay, so I'm going to repeat that question because then this is a key concept. If you understand this, there's nothing to memorize. And this picture will do everything to help you solve, like get this picture in your head. Okay, I got global extrema problems. I understand how to do them. Global extrema only happen at CPs and EPs. Those are X values. I'm going to put those in a list. In this case, there's 4 points to consider. I want to know of those 4, who's the tallest and who's the smallest. Because I'm asking questions about heights, I'm going to plug those X values into the function. I'm not going to plug them into the first derivative. I'm not going to plug them into the second derivative. I'm going to plug them into the function. Thank you, Boomer. Awesome. And this should, again, it should be logical. It should make sense. Nothing to memorize if you just think, what am I trying to do here? When I'm trying to find global extrema, this is the key phrase. They happen at CPs and EPs. Okay, there's only a finite number of points that I have to consider. Even if there were 7 CPs, you only have 9 points, 2 EPs plus 7 CPs. There's only 9 things in your list. Ours is even easier. There's only 4 things in our list. I want to know of those 4, who's the tallest and who's the smallest. So I'm going to take each one of those and plug them into the original function. And we already did a couple of these, so I'm going to use that work already. We already did the left endpoint at -2. So we found that the y value was -2/3. We did the right endpoint over here at 3. We found the height was 6 by plugging into the original function. Right, again, you're always plugging into the original function in the right column. We did this CP over here. This is a CP, right? It has a horizontal tangent line. That was when x was +1. We got that the y value when we plugged in was -2/3. And we have one more point that might be a possible global extrema. We have to check this CP right here at -1. It is a horizontal tangent line. Those are good places to look for extrema. And we're going to see, is it actually an extrema? Well, we know it's only going to be a local from our picture, but let's just see if it makes it, if it is going to be a global. So I plug -1 into the function. So I'm up here. I need to know what f of -1 is. That's the last piece in my table. That's -1 cubed is -1 times 1/3. So that's -1/3, -1 minus, so that becomes positive. So that becomes a +2/3. And that makes sense. It checks from our picture on the graph that we're at -1 and we have a positive y value. Okay, now it's a matter of once you've got, these are the 4 points out of, there's actually infinitely many points right here on that section of the graph. There are infinitely many points slammed in there, right? But I only have to check these 4. That's what the calculus tells us. That's what the extreme value theorem tells us. That's what Fermat's theorem tells us. All these mathematicians came before us and said, okay, you don't need to check infinitely many. You only need to check 4 in this particular example. These 4 have y values. The smallest y values are actually tied right here. These are your 2 global mins. And it also already gives you the points, -2 -2/3. That's the picture right there. 1 -2/3, that's this point right here. And lastly, 6 is the tallest y value, so this is your global max. That also matches on our graph. These 3 points that we have drawn, circling them in red, those are your global extrema of that function on this section of the graph. Were they to change the section of the graph, like make it a little bit longer, we'd say, well, this is no longer the global max. It keeps on going. It's probably that other endpoint over here. So it depends on the interval that they give you. Everything depends on that interval. Okay, so pause for a couple questions.
So I just want to clarify, when you're looking for the global max and min, are you just picking random numbers to plug in to the original function?
Okay, great question, Lauren. You always ask questions that have me summarize. So Lauren's question is, when we're trying to find global extrema, are we just picking random numbers? Well, this is key. This is a key summary. Global extrema, this kind of picture is all you need to think about if I pose you a global extrema problem on a quiz or a test on the final exam, the picture coming in your head should be this table. This table summarizes how you do global extrema problems. You do them by putting your EPs in the list, right? Those are your endpoints. Your left and right endpoint are always given to you in the problem. The other thing you put in your table are critical points. However many your problem has. It might have none, it might have 10. You put them in there, ours had 2. So therefore we have 4 numbers that we need to check their heights of. Why are we just looking at those? Because those are the only places global extrema can happen. Global extrema only happen at CPs and EPs. So I'm going to take that finite number of points. On this section of the graph, there are infinitely many points, but there's only 4 points that I actually need to check because there's only 4 places where I could have global extrema. And then it's just a matter of determining out of these 4 points, who has the tallest y value, who has the smallest y value. So you take those points and plug them back into the original function.
Okay, thank you.
That's perfect, Lauren, because that's what I was going to do to summarize. So that's the last thing. So if you don't have any questions, you're free to go. If you got questions, hang on, and I'll be here for a bit longer. Otherwise, have a great evening, enjoy your dinner, and we'll see you next week.
Thank you.
Sure.
I have a question.
Okay.
Can you summarize one more time? Once you've gotten the f of x, the numbers, how did you determine if they were min or max?
Okay, great. Great to hear your voice, Trinity. You're so helpful with my class. I appreciate that. Okay, so Trinity, what we're trying to do, once we get this column, you're just saying, out of these 4 numbers, what's like the lowest number? The minus 2/3, right? Turns out there's a tie. So those are the smallest out of those, and those will be your global min. And then you're saying who's the tallest, who has the biggest value in this column? That would be the 6, and that would be your global min. I'm sorry, global max.
Okay, what about the positive 2/3?
Okay, yeah, good question. This thing doesn't beat the 6, so it was a candidate that it might be, and the picture shows it's a local max, but it's not a global. And this question is only asking about global.
Okay, that's what I was confused about.
That's a great point, Trinity. Thank you.